Welcome to Series 2 of The Explainer. Now think about it. Geometry taught us how to find the area of a circle, and algebra, well, it taught us how to solve for x. But here's the thing. Those branches of math are basically static. They're great for shapes that just sit there and numbers that don't budge. Calculus, on the other hand, is completely dynamic. It is literally the math of motion, of acceleration, of continuous, unbroken change. So today we're going to explore the two absolute classic, ancient problems that sparked this entire science: the tangent problem and the velocity problem. We'll see exactly how brilliant minds outsmarted a seemingly impossible roadblock to finally understand our universe in motion.
To really wrap our heads around what we mean by dynamic, let's contrast two simple ideas. Picture a still photo of a car. That right there is your static math. Algebra and geometry are fantastic for taking a quick snapshot of a single moment in time, like finding the exact position of that car at one specific second, or maybe calculating the total volume of air inside its tires. But come on, life isn't a photograph, right? Life is a high-speed video. In the real world, things are constantly speeding up, slowing down, and changing direction. To understand that kind of continuous fluid motion, to measure exactly how fast that car is moving at any tiny fraction of a millisecond, we need a totally new set of tools. We need calculus. And the journey to invent those tools, it begins with something called a tangent.
Okay, let's dive into this. The word tangent actually comes from the Latin word tangens, which just translates to touching. Imagine a curve, like a nice smooth parabola, governed by the equation y equals x squared. What we want is to find a straight line that perfectly touches our curve at one single, precise location. Let's call it point P, anchored right at the coordinates 1, 1. This line doesn't slice across the curve, no, it just grazes it perfectly, mirroring the exact slope and direction the curve is heading at that microscopic instant. Finding the slope of this specific grazing line is what we call the legendary tangent problem.
But here's where we hit a massive mathematical roadblock. To find a slope using traditional algebra, we strictly need 2 points. Think back to your classic slope formula, rise over run, or y2 minus y1 divided by x2 minus x1. If we try to use only our single point P, our formula just breaks entirely. We literally don't have a second point to measure against. So mathematicians had to get super clever here. They asked, well, what if we pick a nearby point Q and draw what we call a secant line? A secant line is simply a straight line that intersects the curve at 2 distinct points. Now, it's definitely not a perfect tangent, but it gives us a desperately needed starting point.
Let's visualize this step by step. We've got our target point P perfectly stationed at 1, 1. Next, we pick that second floating point Q somewhere further up the curve, and we connect them with our secant line, PQ. Now, I want you to mentally zoom in on this graph. Watch closely what happens as we move point Q closer and closer to point P along the curve. You'll see the secant line actually starts to rotate. As Q slides down the parabola toward P, the physical distance between the 2 points shrinks, and as they get infinitesimally close to each other, the secant line gracefully approaches the limiting position of the tangent line. It's almost like we're tricking algebra into giving us the slope of a single point by using 2 points that are practically sitting right on top of each other. Now, what's truly fascinating is how the formal math strictly proves our visual intuition. Let's use James Stewart's classic example for this. We're looking at our function, f of x equals x squared, anchored securely at point P 1, 1. Let's calculate the exact slope of that secant line as point Q slowly moves closer. If Q is at an x value of 2, the slope is exactly 3. We slide Q closer to an x of 1.5, and the slope drops to 2.5. Slide it even closer to x equals 1.1, and the slope becomes 2.1. Now let's get extremely close, say x equals 1.01. The slope calculates out to 2.01. Look at that undeniable, beautiful pattern emerging. As x gets progressively closer to 1, the slope undeniably and predictably approaches 2.
And there it is, the number 2. This approaching value is what we officially call our limit. Notice that we didn't actually need to land exactly on point P to figure out what the slope was ultimately going to be. By observing the distinct behavior of the secant line as the distance between P and Q became practically 0, we successfully predicted the true slope of the tangent line. We found the precise, razor-sharp trajectory of the curve at a single, frozen instant. The slope of the tangent line at point P is exactly 2. This concept of the limit is absolutely the foundational spark of all calculus. It is the key that unlocks our ability to measure continuous change.
But wait, you might be wondering right about now, why do we have to go through this whole tedious process of moving Q closer and closer? Why all this complicated talk about approaching a value? Why can't we just plug x equals 1 directly into our trusty slope formula and call it a day? Well, this brings us face to face with a rather dangerous mathematical trap. It's a fundamental paradox that actually puzzled some of the greatest thinkers for centuries before calculus was fully realized.
Here is the strict rule. You absolutely cannot just plug in x equals 1 to find the tangent slope. Why? Because if point Q is exactly on top of point P, their mathematical coordinates are completely identical. You end up calculating 1 minus 1 divided by 1 minus 1. That gives you 0 divided by 0. And in mathematics, 0 divided by 0 is entirely undefined. It breaks the rules of arithmetic. It's a completely meaningless expression. Calculus, brilliantly, allows us to see exactly what happens incredibly close to 1 without ever actually stepping on the landmine of reaching it. This right here is the ultimate heart of a limit. It's the perfect, elegant workaround for that catastrophic 0 over 0 trap.
All right, let's take these abstract graphs and theoretical formulas and pull them right back into the messy, real, physical world. We're going to apply this exact same tangent logic to a classic physics scenario, the velocity problem. Imagine we're standing on the very edge of the upper observation deck of the CN Tower in Toronto, a dizzying 450 meters above the ground below. The wind is howling, we hold out a heavy ball, and we drop it. As it plummets, it steadily speeds up, right? Its velocity is constantly changing, continuously accelerating due to the relentless pull of gravity. Through some incredibly meticulous experiments conducted centuries ago, Galileo discovered the precise mathematical law governing this type of freefall motion. The distance fallen, which we represent as s of t, perfectly equals 4.9 times the amount of time squared. So, if we urgently want to know the exact velocity of that ball after exactly 5 seconds of falling, how do we find it? Think about it for a second. We are dealing with a single instant of time, a mere photograph of motion. Absolutely no time interval has elapsed, which means if we try to calculate speed, which is just distance divided by time, we have an elapsed time of exactly 0. Boom! We are thrown violently right back into the exact same 0 over 0 mathematical trap we just barely escaped with the tangent problem. And this elegantly illustrates the incredibly deep connection between geometry and physical motion. The exact same logic applies to a falling ball as it does to a curved line drawn on a graph. Average velocity, which means measuring the speed over a set period, like from exactly 5 seconds to 5.1 seconds, is just the physical equivalent of a secant slope. We have two distinct points in time. But instantaneous velocity, the exact speed right at the 5-second mark, precisely what a police radar gun would read at that exact fleeting millisecond, is the slope of the tangent line. It's the limit of those average velocities over smaller and smaller time intervals. By calculating the average speed over a tenth of a second, then a hundredth, then a thousandth, we smoothly approach the exact instantaneous limit. Geometry and physics are fundamentally speaking the exact same mathematical language here. So, we've broken through the static world of basic algebra and entered the dynamic, moving universe of calculus. We've seen how pushing secant lines to their absolute limit miraculously reveals the hidden tangents and instantaneous velocities that govern reality. Now, it's your turn to apply these tools. Here is your first challenge of the series. If a rock is thrown into the thin air of Mars with a height represented by the formula y equals 10t minus 1.86 t squared, can you find the average velocity between t equals 1 and t equals 2 seconds? Look closely at the math, think about our secant line slope, and write your calculation down in the comments below. We've seen today how mathematicians effectively trick the universe into revealing its deepest secrets at a single, frozen instant. Next time, we define the limit officially and dive even deeper into the spectacular mechanics of change. If we can freeze a falling ball, what else can we freeze? Thanks for joining this explainer, and I'll catch you in the next one.